Here's today's 5-minute meta.
But what's up with the mask, Doc? A disclaimer. Oh, sorry. Oh, whew. Sorry about the muffled words. So, the question of the week. So, what's up with the mask, Doc? As you can see, and many of you have stated this to me, you're uncomfortable with them, you're tired of wearing them, but very few people and very few actual sources can tell the truth or the facts about why we wear masks, why we shouldn't wear them, where we should, how we should. This week I actually saw an image of someone with a mask sitting under their chin, and I had exposure to someone who literally had part of their mask on top of their head. So this is one of those issues. So to begin, let me just make a disclaimer. The opinions that I share with you in these videos are my own and do not necessarily reflect the opinions of the American Board of Family Medicine, the Arkansas State Medical Board, or my employer, Baxter Regional Hometown Clinics, which is a subsidiary of Baxter Regional Health System. This is going to be part one because of the length. After doing a meta-analysis of 16 studies between 1987 and 2020 regarding various mask usage and scientific issues behind the usage of masks, know that 2 of those studies even were meta-analyses themselves, which reviewed all of the literature available to them. So if I didn't find one of the good studies, it was included in one of the other 2 references that I followed and that I've used here. So we've seen much controversy about masks and whether to wear them or not, when to wear them, why are we still wearing them in places like Arkansas or Stone County where we have no active cases. This has even become a parody meme with something that I actually posted on Facebook this week, as you see here. This was by far the question of the week. But first, a few facts and just a little beautiful science. Understand that viruses are about 1/50th the size of a bacteria. And you see the relative sizes here in nanometers. The large droplets that come from our respiratory tract from sneezing and coughing are up to 125,000 nanometers. The smallest airborne droplets out of our respiratory tract or from speaking are about 1,000 nanometers. The large airborne droplets can hold up to 1 million copies of a virus. The smallest have only about 1/10,000th each of a chance of causing infection because of the nature of the way that they go into the atmosphere and how quickly they dehydrate. But they can hold a few copies, but they're very fragile. There are a lot more of them, however, than some of the larger respiratory droplets that we see, and that you can even see visibly when people speak. Respiratory viruses are all in a size group from about 50 to 150 nanometers. They are all about 100th the size of a red blood cell, and about 10 to 50 times smaller than a bacteria. So how can they be so small? Well, viruses are all similar in one way. They're all parasites that use plant, animal, or human cells to reproduce. And when they do this, they most often kill the cell that they have to hijack so that they can make copies of themselves to pass on. They cannot live on their own. They have only one purpose, to reproduce no matter what the cost. They aren't like cells that have their own genes and own expression of those genes in proteins for nutrition, reproduction, and their own enzymatic activity, such as a liver cell or a digestive cell or a brain cell. They're just like locusts. They just move on and destroy everything that they touch. They produce almost like machines on an assembly line in some cases. And it's just that the assembly line is the cell that they're killing in our lungs, liver, bloodstream, intestine, brain, or other organs while they're on their way to do this. Here's a picture of an influenza virus on an electron photomicrograph. Here's a reproducing adenovirus, by the way, that cause a pink eye. Here's, of course, the thing that we're so familiar with, the copy of the coronavirus molecule in 3D. Here's an HIV virus, and this is the dreaded Ebola virus. You see how large it is and how different its shape is. But you'll notice that all viruses have some things in common. That is, they all have coat proteins that are made of a lipid or fatty layer binding to proteins on the surface. And then they have surface proteins that they use to attach to the cells that they're trying to invade. And between the coat proteins and the surface proteins and the genetics, there are some chemicals that they have and proteins that they can use to assemble or transcribe their RNA or DNA molecules using the materials that they find in whatever cell that they're invading. For example, hepatitis, liver cells; influenza, respiratory cells. You know that bacteria will invade the throat, for example, in strep throat, but bacteria, as we said, are much larger. Every virus seems to have its set of cells that it likes best. Gastroenteritis viruses like the intestinal system. Viruses have to bind to a cell, be absorbed into that cell, or insert themselves, be broken down to reveal and express their genetic material, and then be reassembled by the machinery of the cell so that they can then move on and continue their, as we say, only job, which is to reproduce. Here's a 3D reproduction of a flu virus and its surface proteins interacting with our respiratory cells to attach and gain entrance to our systems. Here is another example from the coronavirus of the molecular and atomic close-up of the model of its spike proteins used to attach to our nose, throat, eye, bronchial, or lung cells, or even our intestinal cells to set up an invasion. Respiratory viruses, so we see adenoviruses, flu viruses, coronavirus, and many others, are shed from an infected person and contacted to a non-infected person in 4 ways. Number 1 is respiratory droplets from coughing or sneezing, or close contact speaking. This is where the mechanism of social distancing as well as the avoidance of contacts comes into play. Also, we see that contact with a surface that has secretions from an infected person can be a source. One of those is called fomites, which are the things such as masks or clothing or inanimate objects that can let that surface material sit so that for several hours at least that virus can live in those secretions, but then be contacted and pass on those viruses to an uninfected host. The last one is inhalation of aerosols that are circulating in the air from a distance from speaking, coughing, or sneezing, and I'll show you some pictures here so that you can understand how that might happen. So masks, if they're helpful, may be shown to be helpful in one of 4 ways. Number 1, limiting contact with secretions as a cue to avoid touching one's face, or cueing others within view that this mask suggests that there's danger afoot, that maybe that person's infected or feels endangered by others. This may be one way that some who would like to maintain that fearful aspect of our society want masks to keep being used even when not needed. We'll deal with that later. But in reality, that is a way that we see, oh, we're in an environment of pandemic or epidemic, people are wearing masks, we need to be careful. And this can be one way that they're helpful. Also, these can block coughed, sneezed, or spoken secretions from an infected person. Or lastly, they can block secretions or expulsions to someone who is uninfected from ourselves. So with this in mind, I'll be back at 10 p.m. with another video that will show the results of all these mask studies. Thanks for your attention, and I'll see you in a little bit.